All right. Hello, everyone, and thank you for joining us for our second session of Crop Talk. A couple housekeeping things. If you are new with us, let me see, it's not. There we go. A big thanks to our Crop Talk team. It takes a lot of us behind the scenes to get this put together for you guys. Our team is led by Jeannie Folk Jones out of our Northwest area agronomist. We also have Craig Dinkle in the Midway District, Stacy Campbell in the Cottonwood District, Sandra Wick in the Post Rock District, Cody Miller in the Phillips Rook District, Lacey Norderman in the Walnut Creek District, Jessica Butters in the Twin Creeks District, myself, Kelsey Lumen in the Golden Prairie District, Aaron Highlands up in Rawlins County, Helen Giefer in Thomas County, and Rihanna Melcher in the Sunflower District. So without further ado, I would like to introduce our speakers for today. We'll start out with John Holman, our K-State Extension agronomist. And then he will be followed by Augustine Obour, our K-State Professor of Soil Management. They'll be talking about available soil water at planting and related management today.
Yeah, very, very happy and pleased to spend some time with you this afternoon talking about soil water and related management. Like I said, I'll go first, and Augustine will follow, and we'll have time for questions. But first of all, when we think about soil available water and crop production, I think this is a really old study, 100-year-old study, but these principles haven't changed for over 100 years. This was looking at alfalfa production from the Texas Panhandle clear up to North Dakota, and what this is showing is that to grow alfalfa in North Dakota, it took about half as much water in North Dakota as it did in Wilson, North Dakota, as it did Dalhart, Texas. And so and that has to do with the water use efficiency and transpiration rate of the crop. So as we have higher evaporation demand in the warmer part of the U.S., that water requirement is higher. And even within Kansas, and I'll show the open pan ET of Kansas, that even varies what we're talking about the state. So we need to have this concept in mind as we start to thinking about what we have available for water and water management. So here is that here's looking at open fan evaporation here in the across the U.S. And you can see, for the large portion of southwest Kansas, extending up in northwest a little bit, with of 90 inches of open pan evaporation. As you get into north central, northwest, that drops to around 85. But so we do see some differences. And some of the long-term work we've done looking at site differences, we do see that crop water functions are different based on whether you're in the northwest or southwest or west or eastern part of the state. So we do have to kind of keep that in mind. So when we give numbers, keep that in context. Residue is also extremely important, and that also relates to um, getting back to the crop water use efficiency. So looking at precipitation storage efficiency, the blue line is at Bushland, Texas, and then the red line is far north in Sidney, Montana, and then the yellow and green line, that's from Akron, Colorado, and North Platte. So what this is saying is, as we increase our crop residue levels out there, we do a better job at storing storing soil water. And as we think about it, and that where that open ET demand is highest down there at Bushland, Texas, the value of that residue is even more important. So we start thinking about Western Kansas, which is also has a very high ET rate. The residue is extremely important, and it would be more important here in Kansas than places north if we're comparing things across the country. This is some data, some long-term data there from Tribune, Kansas. And we've got several studies, but I pulled this data set. This is looking at fallow efficiency based on the tillage method used. We have no-till, reduced-till, and conventional till. Here in inches, no-till stored the most soil water, around 6 inches. Conventional till, about half of that. And so if we look at that fallow efficiency and wheat fallow period, we're talking 24% of that moisture stored, which still isn't great. We're still losing 75% of that water due to evaporation, but a lot better than conventional till. Conventional till only storing about 12% of that soil water. So we think about what has happened in time with no-till systems and reduced till systems coming on board. We've done a better job of storing soil water, and that allowed us to then increase from the historical wheat fallow to wheat sorghum fallow. So we need to keep in mind that the importance of that, keeping that residue there on the soil surface. Now, tillage is still used, and as we think about the difficulties we have with managing weeds, tillage is still a viable tool. Here is looking at different tillage systems: moldboard plow, sweep conventional till, sweep reduced till, and no till. And the black is 0 to 2 days after the tillage implement, and then the gray bar is how much soil is 3 to 5 days later, and this is looking at the amount of water lost. So what this is saying is that right after a tillage event, we see a spike in water loss, but then about 3 to 5 days later, that drops down. In the reduced till system, we are on par here with no till. So, and what that is, we form a mulch layer, and so that stops that evaporation from the soil. So we do have this right after a tillage operation. We do see this loss of soil water, but that mulch layer helps us prevent future water loss. Looking at the fallow efficiency now of a wheat sorghum fallow versus wheat sunflower fallow, the crop choice, and that again, that residue has an effect on fallow efficiency. So in a wheat sorghum fallow system, in that fallow period, we gained about 3 inches and about 2 inches under the sunflower system. So you can see just the crop choice out there and the difference in residue cover of 20% versus 12% in the sunflower system. So again, the getting back to the importance of that residue and the type of residue on the soil surface. This is looking at, I'll kind of walk you through this figure because if you haven't seen this before, it may be a little daunting at first, but what this is with soil depth and going down from 0 to 8 feet, and then this is available soil water starting at dry soil to saturated soil. So what this is saying is here's in the diamond, for example, that this is the wettest soil across all depths. That's a wheat fallow reduced till system. In the dark circle is a wheat sunflower system. It is the driest at all soil depths. And then the wheat grain sorghum fallow is in the round open circle, and wheat corn fallow in the open square. So a couple things here. Again, crop choice has residue has an impact on fallow efficiency. Also, sunflowers do a very good job of extracting soil water. That has a higher matrix potential, so it dries the soil more. So we think about coming back with the next crop that has implications for that, and then cropping intensity. These 3-year rotations are going to have less soil water stored than a wheat fallow system. Looking at the importance of wheat residue now and the following grain sorghum crop yield. So here we have the water storage in inches. Here we have wheat residue increasing, and here we have grain sorghum on the y-axis increasing. So first of all, for yield, as we increase that wheat residue, we increase yellow bar, we increase water storage, and that translates to increased grain sorghum yield. So again, just stressing the importance of that residue and how it affects water storage and how that affects subsequent crop yield. Now, looking at the time of the year and the efficiency within the year, we've also broken that during the different phases. So this would be like a wheat, sorghum, fallow rotation. So from sorghum harvest to July, that's during a cooler time of the year. Also, right after crop is grown, so the soil is fairly dry. That's our highest use efficiency, storing about 29% there. From July to wheat planting, we're actually lose some soil water out of the soil. So due to evaporation, so we're really that period from late there in the fallow cycle is not very efficient and not contributing in most years to subsequent wheat yield. And then crop harvest, if you look at the whole site, the whole fallow period, that's about 21%. So we've done some work looking at how to increase the cropping intensity of that fallow period, recognizing that the late fallow period is not very efficient. And so we'll share some of that information, but where we're at in the state, where you're at in the for the amount of annual precipitation you get, and the year affects kind of how we might manage that fallow period and how we might go about storing that soil water. So, we know that fallow is inefficient, especially from a wheat fallow standpoint. If we're doing a good job of managing that crop residue and storing soil water, a wheat, sorghum, fallow. Like I mentioned, we have done some work there looking at growing short season cover crops during that fallow period. Not Augustine will share some of that data. What at his location there at Hayes, where he's located, more consistently, we do not see a negative impact on crop yields. But where I'm at, further west, we more often than not see a negative impact on subsequent grain crop yield. So that lends us to this a flex fallow concept, and that I'm setting up the stage there for Augustine to talk a little bit more about some flex fallow type practices. This is looking at from some long-term data there at Garden City, looking at cover versus hay. So we've grown some cover, a crop, same type of crop, grown as either cover or hay, and looking at the plant available water after spring cover crop is grown on wheat. What's available for moisture for wheat there at Garden City? Not much difference at the 0 to 3 inch range. Soil depth, but the cover does have slightly more, about 0.03 inches, and about an inch difference in the total profile there at Garden City. Again, at Hayes, a little more favorable growing season precipitation levels. Do not see this big of a difference there at Hayes as we do compared to Garden City, where it's a little bit drier. And here's a lots of different crops, lots of numbers. I want to show you the trend, and I'll point that out. But so for a lot of years, we've grown lots of different cover crops. If we look at the amount of water available at wheat planting, if we use a fallow system, around 8 inches in that profile. And as we increase cropping intensity, or we increase the amount of biomass grown, we decrease the amount of plant available water. So depending on the crop choice we use of a cover crop, we see a decrease in plant available water. And here's the difference in fallow. Anywhere from 0 to 5 inches less available soil water for that next wheat crop. So the type of cover crop, if we're thinking about intensifying that fallow period, the type of cover crop, the amount of biomass that cover crop grows, has an impact on the plant available water for that next wheat crop. But also year impacts this. So here's a couple of different examples looking at plant available water at wheat planting with cover crop biomass. 2010 was a very wet year, and here we don't see any impact on plant available water in 2010 with increasing cover crop biomass. But 2011, We try to forget 2011 and 2012, but if you remember back there, those are some extremely dry years. And there, as we increase that cover crop biomass, saw a pretty sharp drop off in plant available water for that next wheat crop. So the more biomass we grow, the more water we use. We do have seen improvement in precipitation storage efficiency during that fallow period from growing that cover crop, but never enough. Again, in Garden City, to make up for the amount of soil water lost. As you go east in the state, things are more forgiving, and we can make up that difference if we have enough precipitation in our at that in your location. Okay, real simple. Water makes grain. This is looking at available soil water in the profile at planting plus growing season precipitation on wheat yield, and we see this response here pretty high R squared of around 4.7 bushels for every acre inch we store in the soil and receive through growing season precipitation. If we break that down further, this is looking at some long-term data from Tribune, looking at conventional tillage. Again, I mentioned how I showed how earlier in the presentation I showed how conventional tillage stores less soil water and has less residue to minimize evaporation from the soil. So here we see if we look at the equation here, we're about 3 bushels of wheat yield gained for every inch of available water. We look at no-till, 5.2 inches of yield gain for every inch of available water. So again, just comes back to that soil residue cover, and we're picking up additional 2 bushels for every inch of stored soil water. Looking at long-term data there of sorghum yield response to available soil water, around 7 bushels, close to 7 bushels of grain sorghum yield for every inch of available water between what's in the soil and in-season precipitation. And we break that down also looking at conventional tillage versus no-till. Sorghum is very, very yield responsive to no-till. Here in the conventional till, about five bushels per inch of available soil water versus 7.5 bushels for every inch of available soil water. Here's some long-term data we pulled together, and I've pulled yield. I was able to pull yield and moisture data for about 70 years, but looking at the yield improvement in western Kansas, clear back to 1840s. And then we see what has increased the irrigation yield response in the red, and the green is the non-irrigated dryland yield response. And if we look at what factors really drive wheat yield, October precipitation is really one of the largest factors that influence the outcome of wheat yield. So we think about yield components. The first yield component is to just have a stand. So getting a stand established is the most important thing, and that shows up in the down here with October precipitation. So for every inch of precipitation we get in the fall, that equates to about three bushels. If after we get a stand established, then other things start to become also critical for crop yield of wheat. So February precipitation is also extremely important. Early springtime precipitation is important, and then warm springtime temperatures is as important. So what that says is okay, we need to have that precipitation, at least in dry land, early in the growing season to get the crop established and get it growing up and growing, and warmer springtime temps like we're having this year, or a little warmer than normal, as long as we don't get a killing freeze, gets that crop growing, and what that allows us to do is have grain fill during a cooler time of the year. If we have a real cool spring, sometimes we go from cold to hot summer. That really puts stress on that wheat plant and during the grain fill period. So having a longer grain fill, more favorable growing temperatures, that allows that crop to reach higher yield potential. Looking at sorghum versus corn, what this some long-term data from Western Kansas, and what this is saying is where these 2 points. This is sorghum yield here on the y-axis, and on x-axis is corn yield. So what this is saying is that, and this is a one-to-one relationship, and this is the relationship of corn versus sorghum yield. What this is saying at this point, to this side of the one-to-one line favors sorghum yield, and to the right of this line favors sorghum yield, or sorry, corn yield. So at 100 bushel or less yield potential, the yield of sorghum is favored, and if you're in a yield potential of 100 bushel or greater, corn yield is more favorable for that given year. Okay, some concluding thoughts. Again, we just need to try to make the best use of the precipitation storage that we possibly can. Kansas is if we think about us across the whole United States, I mean, we are challenged with some higher evaporation rates, so keeping that ground covered, storing as much water as possible. If we're using tillage, as I mentioned, as I showed there, as infrequent as tillage as possible, because every tillage event causes a pretty sharp increase in evaporation loss, and then just keeping that ground covered. And then what we know, kind of what our system is, what we have, what the fuel we have in the tank, how much soil water we have in the profile, and then kind of that expected growing season precipitation. Then we can kind of expect maybe what our yield potential is for that coming year. We've had a little more success intensifying things when we think about things like forages, because forages require less water than grain crops. So that is been more favorable way to increase the cropping intensity. Um, Augustine will talk a little bit more about flex cropping, so I'm not going to go into much about that. But again, flex cropping, and then just think about how we can keep that residue on there so that we can try to keep that ground covered for those real challenging years. Here's some my contact information is here, so happy to reach out to me, reach out to your county agents. They're well aware of a lot of these things and kind of help make some of those management decisions. Augustine, I'm going to stop sharing and let if there's some questions I could take them. Otherwise, I'll let you put up your presentation.
John, it doesn't look like we have any questions at the moment, so if any roll in, we'll let you know.
Okay,
Can
thank
you
you.
see my slides?
Yes, we
I
can.
can.
All right. Yeah, John, I didn't know that I need to talk about flex cover cropping and stuff, but my name is Augustine Obour. The plan today is to talk about using plant available water to adjust nitrogen rate management decisions in dryland environments. And we're going to use mostly sorghum as an example for this talk. So as John mentioned, in our dryland environment, crop production is highly dependent on plant available water that we can store during the fallow period. So most of our production systems, like winter wheat grain sorghum fallow or winter wheat corn fallow system, will have some form of fallow as part of the rotation. Depending on how you manage the fallow, water storage can be about 20% for our no-till systems that we have, or if you have high residue inputs, this could increase to about 40%. So you are not storing all the water that is received during fallow, but this is very crucial for our production systems because grain crops like wheat, or sorghum. And particularly sorghum can grow very deep into the soil to make use of the plant available water that is stored. And this is very helpful for grain crop production, particularly in dry years. Apart from water, which is very critical for our environment, nitrogen is also very important for crop production in our environment. So one of the things that we see is oftentimes you can apply too much nitrogen to the crop. If you have very little water, that can impact the amount of growth that you get. You can get excessive vegetative growth during the growing season. And if you have less water, you won't have the water needed to finish the crop, and that will impact the yields. If you apply too little nitrogen, and in years where you have a little bit more water stored in the soil, that can reduce the efficiency of the fertilizer apply or reduce the efficiency of the water use in the system. Therefore, matching how much fertilizer you put in the system and to the available water that you have is very important to optimize crop production in our environment. So we have done some studies in haze. These are long-term research plots that we have in haze, looking at how you can manage this water. So some of the things that we do to determine available water in our research environments is very cumbersome. We can take soil samples. We can install soil moisture sensors to accurately determine how much water we have in the soil. But this is cumbersome and time consuming, so growers cannot use this to easily determine water. But what we can do in this case, you can use the Paul Brown probe. This is a picture of the Paul Brown probe. This is a metal rod that you can push into the soil to determine essentially how much moist soil you have. And in dryland environment, the pressure that is required or the force required to push the probe into the ground is directly related to how wet the soil is. So this can give you an idea about how much water you have in the soil. This is a picture showing how you can implement this in the field. And if you know the amount of water in the soil, you can convert this into plant available water based on the texture and some conversion tables that we have. For example, this table here shows the plant available water per foot of moist soil that you measure with a Paul Brown probe. For example, if you have a coarse texture soil, the amount of plant available water will be about 0.5 inches for each foot that you can push the probe into the ground. If you have a silty clay loam soil like we do have in most part of Western Kansas, this will be about 2.2 inches of plant available water. So for example, close to the time of planting, you go in, you push the probe to about 5 feet. If you have like 5 feet in, that was how much depth of moist soil you have. You multiply that by 2 if you have a loamy soil, and that will be about 10 inches of plant available water. So this can be a quicker way of you to determine how much water you have in the soil. And then, like John said, depending on the amount of water that you have, you can make some cropping decisions, what to plant in the production system. But you can also use that to make fertilizer decisions as well. So some of our research that we have done in haze, this particular study was from 1970 to 2002 to look at if we can use plant available water at planting to make nitrogen fertilizer decisions in grain sorghum. So in this study, they had 4 nitrogen rates, 0, 20, 40, and 60 pounds of N per acre. And then at the time of planting, use the Paul Brown probe, push it into the soil to determine the amount of moisture in the soil, and then convert this into plant available water content. We also determine precipitation over the 32 years of the study. So this is some of the data that we collected from that study. Here we are looking at using in-season precipitation to determine how much yields that were produced over the years. And this is actually grouped into yield environments. So very low yielding environment is when grain yields are significantly less than the average. Low yield environments is when it's less than the average, but it's within the errors that were measured within the standard deviation. And then high yielding environment is anything that is greater than the average, and very high yielding environments is significantly greater than the average yields over the 32-year study. So here you can see that in-season precipitation doesn't really predict what kind of yields we are going to get. For example, in one of the years, the growing season precipitation was about 30 inches of rain, but the yields were very low. In other years, you get about 10 inches of rain, and the yields were higher, so high yielded environment in that particular year. On average, we had about 15 inches of precipitation, and the yields it can be low or very high. So we look at available water at planting. If we look at plant available water at planting, then there's a linear relationship between how much water we have at the time of planting and sorghum yields. So when you have about 2 to 4 inches of plant available water at planting, grain sorghum yields will be very low. As you increase the plant available water at planting from 4 to about 8 inches, you are in the area where you have low yields. But when you have over 8 inches of plant available water at planting, then sorghum yields increase significantly. So you can use this kind of information to make fertilizer nitrogen decisions as well. So this data is looking at yield environments and how that impact your fertilizer rates. So on the x-axis here is the amount of fertilizer applied from 0 to 60 pounds per acre, and the y-axis is sorghum yields. The dark line is very low yield environment. So in that scenario, applying fertilizer had no impact on the sorghum yields. However, the red lines here and then the green line and blue lines represent where we have about 20, 40, and 60 pounds per acre. In these conditions, there is response to fertilizer, especially when you are in a high yielding or very high yielding environment. The response to fertilizer is very high. So this is something that we can use to, like I said, make some management decisions as well. So here we plotted the actual plant available water at planting or grain sorghum yields for each of the nitrogen rates. The same kind of lines. The dark line represent where no fertilizer was applied. The red lines is 20 pounds and the green lines is 40 pounds, and the blue line is where we apply 60 pounds of nitrogen per acre. Looking at the x-axis here, when we have about 2 to 6 inches of plant available water, there's not much response to fertilizer. So in this scenario, applying fertilizer under these conditions, when you have less plant available water, did not improve yields. However, at 8 inches or above, then we begin to see a separation in our nitrogen rates. In fact, if you look at the equations derived from this fertilizer response, when you had about 1 inch of rainfall with no fertilizer applied, 1 inch of plant available water at planting with no fertilizer applied, sorghum yields were about 3.8 bushels per acre. When we apply about 60 pounds of N for each inch of plant available water, sorghum yields increase about 8.2 bushels per acre. This is similar to what John already shared, that we plant available water in those studies that were done in Tribune was around 7.5 bushels per acre per inch of plant available water at planting. So we can use this kind of information to make adjustments. So if our plant available water at planting is less than, in this case, less than 8 inches, then applying just about 40 pounds of N will be adequate. But if we have more plant available water at planting, then we can add more nitrogen fertilizer to take advantage of the water that we have to increase grain yields. Then we also looking at the in-season precipitation. Even though there is a relationship, the in-season precipitation explains just about 4 to about 18% of the variability in sorghum yields. For example, if you look at the previous slide, when we apply 60 pounds of N, the green bar, we were increasing sorghum yields about for each inch of plant available water, the sorghum yields were about 8.2 bushels per acre. Here, if you look at in-season precipitation, if you have 1 inch of in-season precipitation and apply 60 pounds of N, the yield increase about 2.2 bushels per acre. So this shows that in that scenario, the in-season precipitation is not a better determinant of the yields. It has minimal impact on grain sorghum yields. This is another way of looking at the same data. This is a 3D view of the data, looking at in-season precipitation and available soil water at planting. Even if we have about 25 inches of in-season precipitation, the yields were around about 40 bushels per acre. As plant available water at planting increases, we are significantly increasing the grain sorghum yields. And this is applicable to corn as well. So if we don't convert the data, just looking at just the soil moisture depth that we measure with the Paul Brown probe, so this is just those values presented here in the x-axis against sorghum yields. Once again, looking at the same nitrogen rates. So here you can see the same kind of data. If we have less than 3 inches of moist soil, then applying fertilizer, we are not seeing that much response. However, after 42 inches, we are seeing significant response to our fertilizer. There's a linear relationship. This is about 7 to 12 inches of in-season precipitation. If we have a more in-season precipitation, like 12 to 16 inches, we're getting the same kind of response. We seeing that after 32 or 42 inches of soil moisture depth, sorghum yields significantly increase with fertilizer application. Then more recently, we've been looking at updating our nitrogen fertilizer recommendations. We've been doing experiments in Raleigh County, Ellis County here in Hayes, where I'm located. We have other sites in Franklin and Republic counties. This work is being led by Durva, our soil fertility specialist on campus. We have a grad student working on this project with us as well. We're looking at the rainfall, which is the rainfall observed over the growing season, which is the blue bars or blue lines. The orange bars or lines represent the long-term normal precipitation. In most years in Hayes, precipitation except 2021 was significantly less than the long-term average precipitation. So this is kind of a low-yielding environment compared to Raleigh County, where most of the time we have normal precipitation except in 2023. So when we combine all these data, so by the way, this is rainfall amounts from March through September. So when we look at that precipitation amount received from the fallow period before we plant from March all the way, and then from May through September combined, we graph that with grain sorghum yields, and the yields plateaued about 17 inches, 17.4 inches. So if you have 17.4 inches over that growth period, you hitting yields about 115 bushels per acre. However, in Ellis County, in Hayes, we were almost around 14 to 15 inches of precipitation, and that is yields around 85 bushels per acre. So you can use some of this information to know how much rain you have and how much water potentially you will store, and then you can determine if you are going to be in low yielding or high yielding environments, and then you can adjust your nitrogen rates, because if you the yield environments will determine how much response you have to fertilizer. So we look at some of the nitrogen uptake response from the size My left side is the low precipitation environments in Ellis County, Hayes, 2022 and 2024. If you look at 2022, nitrogen uptakes were less than 50 pounds per acre. So in this case, applying nitrogen did not have any impact on nitrogen uptake by sorghum. However, 2024 was a little bit wet. We had a little bit more rain than 2022. But here again, our nitrogen uptakes were less than 100 pounds per acre. And this peaked at about 60 pounds per acre nitrogen application. Even that, it wasn't different from when we applied 30 pounds of nitrogen per acre. So looking at the yield environment, we can cut back on fertilizer nitrogen applied. If you look at Riley County, for example, in 2021, we had a little bit more rainfall, and nitrogen uptake was around 100 to 110 pounds per acre. In this case, applying about 120 pounds of nitrogen maximize nitrogen uptake in sorghum. And even in that case, 90 pounds per acre resulted in similar nitrogen uptake. So based on the yield environment, like I keep saying, you should be able to make some management decisions regarding fertilizer application. So some summary thoughts here, as John has said initially, and based on some of the long-term data that we've had here in Hayes, determine plant available water at planting is very useful. It can help to manage nitrogen fertilizer because the response are going to be dependent on how much water you have in the soil, particularly in dryland environments. The distribution of rainfall is very important. That also impact how much nitrogen is taken up by the plant. If you have more precipitation in the earlier months, like for sorghum and corn, between March through May, if you have enough rainfall and increase plant available water at planting, and that can influence how much nitrogen is taken up by the plant. In low yielding environments, nitrogen removal rates are very, very low, and cutting back nitrogen will be very useful. So, in effect, for nitrogen fertilizer management in dryland environments, you can adjust your nitrogen rates based on yield goals, which is important, knowing how much the target yields that you have. Residual nitrogen is very important, but you need to also consider how much plant available water you have at planting. If you have enough water in the soil at the time of planting, you can make your fertilizer nitrogen recommendations accordingly. If you have less plant available water, cutting back will be very useful as well. So thank you very much. This is all I have. Once again, my name is Augustine Obour. I'm based here at the Ag Research Center in Hayes, and my colleague, Dr. Holman, is also based in Garden City. The work that we have been doing here is supported by funding from the Ogalala Aquifer Grant Program. We also get funding from NRCS, and Northcentral grants are supported some of the work that we've done in Western Kansas. I'll stop here and take any questions that you may have.
We have a question in the chat. Is available soil water information published anywhere in real time for various locations?
Yeah, I will take this. We do have the Mesonet, the Kansas Mesonet. We do have, if you look at the size, it will give you information on soil water content, but this will be very shallow. So the easier way to do this is actually, if you get a hold of a Paul Brown probe, you can probe the soil and know how much water you have. And you can use these tables to know the plant available water content. I think the extension offices may have some of these probes that you can use to actually measure this in real time on your field.
I might just add, yeah, like Augustine said, the Kansas Mesonet available. And those are in perennial grass, and so depending on your system, right? If you're using tillage or not, how much crop residue, that all affects that amount. But what Augustine has said is right. You take a Paul Brown probe, and then um, this information will be available later. You could take that probe and then measure how deep it goes, and look at the amount. That table will give you an idea. Take it times 0.2, and that'll give you an idea of how much soil water you've got to work with. And then growing season precipitation. We've got the mesonet. You can look at a time series and see what you might expect for an area, and then that can give you an idea of what the estimated yield could be.
I would just chime in here just a little bit that I do have a Paul Brown probe in my office in Colby. So if anybody's interested and you're in the northwest part of the state, let me know. We can get it for you. Augustine and John, when you see the Paul Brown probe, it looks like just a cylinder that's going into the ground, but it has a little screw end on it. When folks are using that to put it in the ground, are you just pushing straight in? Or are you also twisting it when you're trying to get to depth?
Well,
It,
I'll say my comments, and then I'll let Augustine. Um, there's two kinds of probes out there you might find. One probe would be a long rod with a small ball on the end, and then the Paul Brown probe was actually that was a scientist that was actually a USDA or ARS scientist years and years ago, located originally at Hayes, and then moved to Montana. And he was, I mean, this was maybe Augustine knows, but this work was kind of pioneered almost darn near 100 years ago. But there is a difference there. What I have found between the two types of probes, the one with a small ball on the end and rod, seems like you can shove that in the ground a little bit farther than the Paul Brown probe. So because of that, I kind of like I think the traditional Paul Brown probe seems for me to give a little more uh, accurate reading. Also, the type of person, if you're 100 pounds versus 250 pounds, and you're going to see that'll add a few inches there too. So, kind of take that into account. But Paul Brown probe, if you use that, and then I usually shove that in the ground, and then um, you can, but I'm not twisting as I go. Just shove it in, and then maybe give it a few turns there at the end. Pull that soil out. You can get a sample, see what it looks like, kind of at that depth.
yeah, so I think you don't have to twist it, and then you also have to push it slowly. You don't have to just, if you force it, it will give you the false reading, but it's not accurate, right? So it's trying to give you some kind of estimate, but it helps. It's better than not having anything. But if you want to do this too, if you want to estimate this from field to field, you want to be have just one person do it so that if there's errors, it's going to be replicated across. You want to take more than one probe readings. At least I'll recommend taking more than five, just a minimum of five. Then you can average it, a minimum of five from different spot because water movement varies from side to side, right? So within maybe 10 feet, there could be variability in water content. So taking more than five probe measurements uh, will be what I'll recommend. So you average it to get an idea of what the soil water content is.
Good deal. Thank you guys for talking through that just a little bit more on actually taking these measurements. Helen, Kelsey, do we have any more questions in the Q&A?
We
I'm
do
not
not. Doesn't
seeing
look like it.
anything.
Okay, I have one more question for you guys that was sent to me on an email. Augustine, the chart that you put up that had the available soil water at planting and then followed by the in-season precipitation, it seemed like, if we didn't have moisture early, but then would catch some during the growing season, it didn't seem like our grain sorghum was quite as responsive. We weren't seeing some of those yields tick up as much. Do you want to comment a little bit more on that?
Yeah, so the question is, we have seen that the growing season perspective, even though you get the rainfall during the growing season, it doesn't impact the yield that much. And this has to do with establishment of the crop. You need the moisture to get a crop up, to get it growing. So, for instance, if you don't have enough rainfall so in March through May or early June, so if you rely on growing season precipitation, you should be somewhere in June. If the rain comes in later months, sometimes you can get the rainfall comes in just 5 inches in July and it doesn't rain again. So that will not have that much impact on your yields. But if the rainfall comes in the early part, like you plant this in first week in June, and then if it rain right after that, then it can have more impact than rainfall that will come in the later part. So you have rainfall towards the end of July or August. At that point, you've already lost the yields. And then one thing that we have even found also, the store water content is very, very important. Even if it's dry at the beginning, the sorghum or particularly sorghum can put up deeper roots into the soil. So when you get into July, when we don't even get the rain, it will rely on the soil water in content in the soil for growth. And we see this between our no-till fields and then our conventional till fields. The same field, the same plot rep, you can see that the no-till fields will not be water stressed for about 2 weeks while the conventional till field is showing water stress. So within 2 weeks, we can catch some rain and then the crops will recover. But the no-till field will still stay greener, a little bit better, holding the plants better than where we had a conventional till plants. So the amount of water in the soil is very, very critical for our environment. Don, do
Great.
you have anything to add?
Well, you hit on it there. I'll make one comment that yeah, the no-till could show take longer to show crop stress than the no-till, and that's also part of the reason why we see that beginning soil water have more impact on crop yield because um, and that has to do with, again, the storage, capture, and use efficiency. So if it's in the ground, it's there, we can make use of it, it's 100%. The rain we get during the growing season, we lose some of that to evaporation. It's not stored till it's in the soil water. So, at best, maybe we're, 50% efficiency of that rainfall. So that's why it's less effective for crop yield, and that's why again, the importance of that residue, no-till, keeping that ground covered, reducing that evaporation. Not only is that extremely important during the fallow period, but as Augustine said, that's also very important during the growing season of that crop too.
Good deal. Thank you guys for diving into that just a little bit deeper to kind of understand a little bit better, how that in season, how it's important, but we really need the stored soil moisture to get us rolling on things. So thank you for diving into that a little bit deeper. Okay, Lacey, do you want to close us out?
Okay. Thank you again, Augustine and John, for your presentation.